Okay, greetings everyone. Welcome into my channel. Happy Friday. I am Professor L, and this is a live stream for Math Help. So, yeah, historically, on Fridays, usually I have technical issues with my camera or my live stream. So, I am anticipating having some issues probably just because of that. Typically on a Friday, my live stream will cut short. So, yeah, we'll just see how it goes and hopefully not. But yeah, if you're out there and you need help with your math homework, yeah, you can put your math problem in the chat. And if I see it, I'll be trying to look for it. I will do my best to work it out, and we can do math together if you want to. But no better time than a Friday evening to be hanging out and doing some math. Um, but yeah, if I don't have any students with math problems, then I will just be hanging out, getting some practice in working on my board and discussing a math topic. I have decided to move on from polynomial land. So I'm going to go ahead and attempt to solve and graph a system, a nonlinear system of equations, and we'll just see how it goes. And so I'm going to go ahead and get into it. And yeah, hopefully I have cooperation from my technology. All right, so let's see. I have a system picked out that looked pretty cool. It's a parabola intersected by a line. So we have a quadratic function and a linear function in this system. And it was a toss-up between that and the circle. If this goes well, and I am so inclined, maybe I'll do the circle one next. And how to solve these systems. So typically a system of equations, so every equation in the world produces a graph. And what the graph is it's a pictorial representation of that function and the behavior in the Cartesian coordinate system. So in order for you to have a solution to your equation, let's see which ones I have. Let's see. All right, what am I doing? I've been doing polynomials for so long. We have y equals x squared, and let's see what it is, minus 6x plus 9. And y equals x plus 3. Y equals x plus 3. All right, so we have a second degree polynomial, which is a quadratic, and we have a line. And I'm going to go ahead and sketch my Cartesian coordinate system here real quick, because I do plan on sketching the graph of this thing. And what we have really quick, if we go ahead and analyze this function first, which it's not really necessary to solve, but just looking at this function right here, we have a y-intercept x comma 1. Let's just get a couple points here. We have a y-intercept when, see, x is 0, y is 9. And then this one probably factors, let's see, x squared minus 6x plus 9. What is that, 3 and 3? So we've got x minus 3x minus 3. So this is x minus 3 quantity squared. All right, so there is math theory behind graphing polynomials, that if you have a square, that means it's sitting on the x-axis. So we have it looks like call that 9. So we have a y-intercept of 9. And then we have a bounce at, well, the factor is going to be x minus 3 equals 0. So adding 3 to both sides, you're going to get your 0 at x equals 3. So we have 3. So we have our parabolas sitting on the x-axis here at 3. And then it's going through 9. All right, so we have this kind of thing going on. 1, 2, 3, 4. Okay, so we've already kind of got the behavior of this function. And then we have this function here, this y equals x plus 3. This is a, remember slope, m is rise over run. So you've got a 1 over 1 with a y-intercept of 3 for your linear function. So you've got this point here at 0, 3. Let's see, we'll put this table over here. And let's see, when x is 0, y is 3. And then if we have even a couple more points, we've got rise over run. So that's going to be 4, 1, 5, 2. 6, 3. Because putting 1, you get 4. Putting 2 in for x, you're going to get 5. Putting 3 in for x, you're going to get 6. Where is my ruler? So I can get a good straight line. So we've got this linear function here. And we'll go ahead and calculate, let's see what the x-intercept is when y is 0. I'll go ahead and get out of order here. And when y is 0, what's this function do? So 0 equals x plus 3. So that's at negative 3. X plus 3 equals 0. So subtracting 3 from both sides, you're going to get x equals negative 3 here. One, 2, 3. Okay. And let's see here, go back to our parabola here, and we'll get some more points on here. We'll see 1, 2, 3. We already know 3. That's our 0. 4, and we have 5 on the graph, but that might be good enough. Okay. And then also what we could do, oh yeah, so the vertex is at 3, 0. Because this is already in vertex form. So vertex form, that y equals a times x minus h y squared plus k. So we have that vertex form. So since this is already a perfect square, then that puts k at 0. So it's going to be so it'll be x minus 3 will be x plus 3. No, it's minus. Because we've already graphed it. So since we have this, it puts our k at 0. So our vertex is at h comma k. So it's going to be positive 3 comma 0, which we already have that. And then let's go ahead and just plug in a couple of times for this function. So here, I can put it here. We'll have room. So y equals, when x equals 1, let's plug in. So we have 1 squared minus 6 times 1 plus 9. So that is 1 minus 6 plus 9. So 10 minus 6, was that 4? And then we'll do when x equals 2, y equals 2 squared minus 6 times 2 plus 9. 2 squared is 4, minus 6 times 2, which is 12, plus 9. And I like to add the positives and then subtract the negatives. So 9 and 4 is 13. Minus 12 is 1. All right, let's go ahead and plug those points in, and then we'll figure out what we're going to do next. 1 comma 4 is on there. And that is definitely a point in common. And then 2 comma 1. 2 comma 1 is here. So we've got to connect the dots and make a pretty graph. And then I might want to go ahead and figure out what negative 1's doing. What's just to see, but it's probably there somewhere. And then let me step back and see what I'm going to do. Yeah, so we have a symmetrical graph. So that means that most likely it's going to be 4 comma 1 as well. Let's go ahead and plug in 4 and see. So x equals 4. Y equals 4 squared minus 6 times 4 plus 9. That's going to give me 16 minus 24 plus 9. Yeah, so that's 16 and 9 is 25 minus 24, which is 1. Good. So then that means at 5, we're probably back to 4. I'm gonna go ahead and do it real quick just to make sure. I think I can fit it in here when x equals 5. Just for fun. Y equals 5 squared. I like patterns, so 5 squared minus 6 times 5 plus 9, and the predictability of it. So I was estimating that I thought it was gonna be, see, I thought it was gonna be at 4. So let's see if we get 4. 5 squared is 25 minus 30 plus 9. So that is, yeah, so that's going to be 34 minus 30 equals 4. Good. All right. Cool. And it's just because of the symmetry. Okay. Involved there. And so then, let's see, at 5, so technically at 6, we should be at 9. Okay, we're going to do that one. Let's do 6 real quick. It's relevant. And I'll put it in here. X equals 6. X equals 6. Okay. So we have y equals 6 squared minus 6 times 6 plus 9. And I'm guessing that we're at 9 by 9. Look at that. Looks a little rough there. We'll just see. If I'm wrong, I change it. But 6 times 6 is 36. Look, minus 36 plus 9. Good. So that is going to be plus 9, like anticipated. So let's see if I can get it a little bit more accurate. Again, it's just a rough sketch. So wait, it looks like it might be right on the line. So I'm just curious. We're going to plug in our function here, our line, at x equals 6. And we get 9. So we've got those 2 points in common. So the solution to a system of equations essentially is the points in common. It's where graphically these two functions are intersecting. So graphically, we can see that there's 2 solutions to this equation. We can see a clear intersection at 1, 4, and we can see the other clear intersection is at 6, 9. And this is actually the solution to the system. We can verify that graphically. I think it's important to first solve the system graphically so that you can, a picture is worth 1,000 words, and that's true for math too. So if you have a picture, you can see those clear intersections. You know there's a solution because sometimes the graphs don't intersect. So if they don't intersect at all, the 2 functions, there's not going to be a solution to the system. And that's also good to know. If you don't have a solution to your system, you want to know that. but we can see clearly two intersections here, and that was a lot of work to verify that graphically, but that was fun. Again, it's exploring the lost art of graphing something without the use of tools. So, all right. What I'm going to do now is I'm going to erase all this work, and I want to solve this system now algebraically. So yeah, I have the graph, and it looks good. We used a lot of theory behind graphing it, and I honestly don't know why I chose to graph it first. I just did. Out of maybe it was instinct. I'm not sure. Maybe I just like graphing things. Okay. So a little bit of algebra to solve the system. What we could do is, so usually the rules for solving systems apply. It's the same rules as solving matrices, because essentially that's what it is. It's introduction to essentially matrices, but matrices are linear systems, and you can have any two functions that you want could be a system. So there's a lot of functions out there that are not linear. And in this case, we have a parabola and a line. But typically the rules would still apply, where you could add the equations, or you could make a substitution typically, and either one you could do. If I since they're already set equal to y, and the easiest thing it looks like for me to do would be just to, well, if they're both equal to y, then I can set them equal to each other. And so that's kind of what I would do. X plus 3 equals x squared minus 6x plus 9. And then a little bit of algebra, and I'm comfortable solving second degree polynomials. They're quadratics, I'm comfortable. So what we're going to do is we're going to figure out how we're going to solve this, and remembering the three methods. So if you're wanting to solve it, find your zeros, essentially what you have to do is you have to set it equal to 0. So if I do that, if I subtract the quantity x plus 3 for both sides, then I'll be able to do that. So that's essentially what I will do. So I will say minus x minus 3, and then minus x minus 3. And you get 0 equals x squared. And then combine your linear terms. That's negative 7x. And then 9 minus 3 is plus 6. And then I think this one factors. So you have 0. And I think that's x. What is that? 6 and 1 minus. And we verified again. Let's go ahead and write these. I just thought of something. We found these solutions where these graphs intersect. This is 1, 4, and the other one was 6, 9. So when you solve this system algebraically, you're going to get these ordered pairs. You're first solving for x. And what this is saying is, because when you have these two factors and you have them set equal to 0, there's two values for x that satisfy that equation. So you're going to have x minus 1 equals 0 and x minus 6 equals 0. And then a one-step equation, just adding 1 to both sides, you're going to get x equals 1. And here, similarly, inversely, adding 6 to both sides, you're going to get x equals 6. And these are the two values for x that satisfies this equation, this one. And so since we've found where these two equations are equal, and we're talking about the domain value, then we're going to take this value for x, and we're going to plug in to either one of these equations. They both must satisfy. So you should be able to plug in. This one is much easier to evaluate, so we could use that one, but this one should also work. So if I plug when x equals 1 here into this top equation, 1 squared minus 6 times 1 plus 9, that's going to be positive. Wait, 1 minus, yeah, I had it. It was positive 3. When x is 1, y equals 1. Yeah, positive 3 plus 1 is 4. So you should get 1/10. I'm over here trying to do mental math and I'm getting ahead of myself here. 1 plus 9. I'll just show. That's part of me not needing to be lazy and just go ahead and write it out. And that's why I'm here, really, is to get practice doing that. Okay, 1 squared is 1, minus 6 times 1 is 6 plus 9. So that is 10 minus 6, which is 4. So we have when x is 1, y equal 4. So we have that order pair 1, 4. And we already found that graphically. But this is just one of the methods of solving it. All right. And then 6, we can use the bottom one just to show you that both of them work. Y equals x plus 3. When x is 6, you get y equals 6 plus 3, and that is 9. So y equal 9 when x is 6. So we've got that order pair, 6, 9. The x component and the y component. All right, good. And that worked out. I was kind of worried about what the graph would look like on the board, whether I would be able to get a clean intersection, because I don't have a grid. There's not like perfect intersections. So we're just rough sketching it. But I'm happy with it. I think it looked good. And I wasn't trying to do too much, since I don't have any students tonight. I'll probably go ahead and call it good. Yeah, it's been a long week and there's thunderstorms, and I can see like the lights like flickering at times. So I'm really surprised that my connection held up, and I'll just celebrate that as a win. And yeah, maybe I'll grab another system. Maybe I was looking at this other one that I wanted to do. It was a circle that looked pretty cool. And it wasn't a terrible circle. It was, just about the origin. So centered at the origin. So it's a pretty simple equation. And yeah, maybe I'll graph that one. I'm trying to kind of play it by ear and just, not getting too big of a plan for the future of this live stream. We're just taking it day by day and trying to have fun with it. So yeah, um, it's Friday, so I will have the weekend to think about it, and I will be back Monday. Again, this project is for fun and hopefully in the process helping some students out there um, get more comfortable with math. And if I can do it, you can do it for sure. But yeah, so I'll quit rambling on and get back to my Friday festivities. And um, yeah, I guess we'll end the live stream for now. And but as a reminder, I will be back here Monday through Friday. This from 6 p.m. to 7 p.m. Central Time, and just hanging out on my board and offering up this space to students if they if you need help with your math. So yeah, we'll just see what happens. I hope you have a wonderful weekend, and just want to say thank you so much for watching my videos, and yeah, I will see you next time. Bye.